Hello, we are Group 6, and this is Micro Project 1. Our product is the jet engine turbine blade. Little background on turbine blades. They started in the 1960s. Pratt and Whitney recognized that they needed a better turbine blade design, and they understood that to get the best efficiency out of a jet engine, it needed to operate at high strength, high temp, and have high corrosion resistance. And all of that kind of fueled the incentive to make a single crystal turbine blade. This is a face-centered cubic type blade, and then the columnar grains are aligned with the major stress axis. And why that's a big deal is because as the turbine spins, the stress will go with the grains, and which allows it to deal with much more stress within the engine. And then in the upper right-hand corner, you see a picture of the transformation where on the left-hand side, the turbine blade starts as equiaxed, and then you can see the directional crystals, and then the final product where it turns into a single crystal.
All right, so what are turbine blades used for? They basically create the thrust for jet engines, which are used in nearly every commercial and military jet that flies today. So as you can see in the top right-hand picture, the turbine blades are located in the back of the jet engine, and they are located behind the compressor and the combustion chamber. So the compressor creates hot pressurized air that runs through the turbine blades, and the blades propel the air out of the back of the engine, which creates the thrust. Another interesting thing that turbine blades do is they cool the air as it passes through them. So if you can see the picture on the bottom right-hand corner, there's like little holes that go throughout the blade itself, and that acts to help cool the blade to take some of the pressure off it, and so it doesn't have to operate at such a high temperature. And then the turbine blade shaft is also connected to the compressor, so when the turbine blade spins, it also spins the compressor.
So a little bit about diffusion and manufacturing. We know that the grain boundaries are the weakest points on the structure. And to minimize these weak points, they heat the material to a super high temperature way above the boiling point, and then they slowly cool the material. They have molds that they then pour the material into, and below it we have a grain selector, which is pictured at the top left. And a grain selector is put on there, and it ensures at the end that the blade or the material is one total grain. And by doing this, it minimizes weakest points, and the melting temperature of the material is raised significantly. And then a little bit about mechanical properties. By changing the cooling time, you can optimize your different properties, so toughness and strain, to ensure that your blade is useful for what you're using it for.
All right, important aspects of diffusion. First, grain boundaries are an important thing to know in order to optimize the jet engine turbine blade's properties. An image of grain boundaries is shown to the right. Grain boundaries are defects in the crystal structure. These defects are minimized in order to create a single crystal which can withstand temperatures beyond a material's melting point. Next, the influence of temperature on diffusion is important. An increase in temperature causes the diffusion coefficient to increase as well. And the higher the diffusion coefficient means the faster the rate of diffusion. And understanding the effects of temperature on diffusion can allow the process of creating a single crystal turbine blade to be quicker.
Earlier this semester, we covered crystal structures in Chapter 3. The nickel used in the superalloy that makes up a turbine blade has face-centered cubic crystal structure, which just means that there's an atom at each corner as well as the center of each side. When other metallic elements are alloyed with the nickel, a microstructure is produced, and when this structure is equally distributed in the larger alloy, it gains some of the beneficial properties discussed earlier, such as stabilization at higher temps. Another topic we covered was interfacial defects in Chapter 5, specifically grain boundaries. Before the creation of single crystal blades, the conventionally cast turbine blades consist of grains that formed during solidification of the casting mold. This just meant that each grain would have a slightly different crystal lattice orientation than its neighbor, which caused interfaces between the crystals to not be aligned. This just meant that life of the blades would be shortened due to the corrosion and cracks forming at grain boundaries. In a single crystal, all unit cells interlock in the same way and have the same orientation. This completely eliminated grain boundaries, and this is basically just done in a complex process that includes casting blades with internal cooling channels as well as zones for different compositions and crystallographic structures.
Yeah, and then this leads us into just some key points and takeaways from single crystal jet engine blades. And a huge one is just the advances in the composition of the crystals, going from polycrystalline, then directional solidification, then finally developing single crystals. And a cool example of an aircraft that utilizes this technology is the French Rafale fighter jet. And this manufacturing process is extremely delicate. As we learned earlier, any disruption in the cooling can introduce secondary crystals. And from what we've learned throughout the semester, creating a single crystal is a very significant accomplishment, just because we know the prevalence of vacancies and other grain boundaries and defects. And another major thing to sort of take away from this is the development of new blades. There's always going to be development of blades that can function at higher stresses and temperatures. And lastly, an interesting fact about all this is in each individual blade of a turbine jet engine, each blade is supplying about as much power as an entire race car engine.